just want to remind you of the main facts. So the first thing you have to do is, because we're going to have to be doing it several times today, that's the system we're trying to solve. And the first thing you have to do is find the characteristic equation, which in its general form, although this is not the form you should use for 2 by 2, is a minus lambda I equals 0. And its roots are the eigenvalues. And then with the eigenvalues, each eigenvalue, you then have to calculate its eigenvector, which you do by solving the system a minus lambda 1, let's say, times I alpha equals 0, because the solution is the eigenvector alpha 1. And then the final solution that you make out of the two of them is alpha looks like alpha 1 times e to the lambda 1t. Of course, you do that for each eigenvalue. You get the associated eigenvector, and then the general solution is made up out of a linear combination of these guys, individual guys, with constant coefficients. The lecture today is devoted to the two cases where things do not go as smoothly as they seem to in the homework problems you've been doing up till now. The first one will take probably most of the period, so it deals with what happens when an eigenvalue gets repeated. But I think since the situation is a little more complicated than it is where the case of a characteristic root gets repeated in the case of a second-order equation, as we saw it, you know what to do in that case. Here, there are different possibilities, and I thought the best thing to do would be to illustrate them on an example. Okay, so here's a problem. It came out of a mild nightmare, but I won't bore you with the details. Anyway, we have this circular fish tank. It's a very modern fish tank. It's divided into 3 compartments because one holds Siamese fighting fish and one goldfish and one. They shouldn't eat each other. It's going to be a simple temperature problem. The 3 actually compartments have to be kept at different temperatures because, one is for tropical fish and one is for Arctic fish and one is for everyday garden variety fish. But the guy forgets to turn on the heater, and so the temperatures start out what they're supposed to be: tropical, icy, and normal. But as the day wears on, of course, the 3 compartments trade their heat and sort of tend to all end up at the same temperature. So we're going to let xi equal the temperature in tank I. Now, these are separated from each other by glass things. Everything's identical. Each has the same volume, and the same glass partition separates them out, and no heat can escape through. This is very well insulated with very double thick thermopane glass or something like that. So you can see in, but you can't. Heat can't get out very well. So heat essentially is conducted from one of these cells to the other. And let's assume that the water in each tank is kept stirred up because the fish are swimming around in it. That should be a pretty decent way of stirring a fish tank. So the question is, how do each of these is a function of time? And I want to know how they behave over time. So find these functions. Okay, well, we're going to find them as solutions to differential equations. And the differential equations aren't hard to set up. They're very much like the diffusion equation you had for homework or the equations we studied in the beginning of the term. Let's do one carefully because the others go exactly the same way. What determines the flow, the change in temperature? Well, it's the conductivity across the barriers, but there are 2 barriers because heat can flow into this first cell both from this guy and it can flow across this glass pane from the other cells. So we have to take account of both of those possibilities. It's like in your homework, the little diffusion cell that was in the middle could get contributions from both sides, whereas the two guys on the end could only get contribution from one. But here, nobody's on the end. It's a circular table. Everyone's dining equally. And so we have to, everybody can get input from the other two cells. So x1 prime is some constant of conductivity times the temperature difference between cell 3, tank 3, and tank 1. And then there's another term which comes from tank 2. So A times tank 2 minus the temperature difference, tank 2 minus tank 1. Okay, let's write this out. Remember, there'll be other equations too, but instead of doing this, let's do a more careful job with this first equation. When I write it out, remember, the important thing is you're going to have x1, x2, x3 down the left, so they have to occur in the same order on the right in order to use these standard eigenvalue techniques. So the coefficient of x1 is going to be minus ax1, and then another minus ax1. In other words, it's going to be minus 2ax1. And then the x2 term will be plus ax2, and the x3 term will be plus ax3. Well, you can see now, so that's the equation for x1 prime in terms of the other variables. But there is no symmetry. There's no difference between this tank, that tank, and that tank as far as the differential equations are concerned. And therefore, I can get the equations for the other two tanks by just changing 1 to 2, and just switching the letters, just switching the subscripts. So when I finally do it all, the equations are going to be, I'll write them out first out as a system. x1 prime is, let's take a equal 1, because I'm going to want to solve them numerically, and I want you to be able to concentrate on what's important, what's new now, and not to fuss with I don't want to have an extra a floating around everywhere with contributing nothing but a mild confusion to the proceedings. So x1 prime, I'm going to take a equal 1 and simply write it minus 2x1 plus x2 plus x3. And so now, what would the equation for x2 prime be? Well, here, x2 plays the role that x1 played before, and the only way to tell you that x1 was the main guy here was it occurred with a coefficient -2, whereas the other guys occurred with coefficient 1. So that must be what happens here too. This, since x2 prime is our main man, this is x minus x2, and this must be x1 plus, and here, plus x3. And finally, the last one is no different. x3 prime is x1 plus x2, and now it's the x3 that should get -2 for the coefficient. So there's a perfectly reasonable looking set of equations. It doesn't, just how reasonable they are depends upon what their characteristic polynomial turns out to be. And as all the work in these problems is trying to find nice models where you won't have to use MATLAB to calculate the roots, the eigenvalues, the roots of the characteristic polynomial. So we have to now find the characteristic polynomial. The matrix that we're talking about is the matrix, well, let's right away write A minus lambda I. I can't use the trace and determinant form for this equation because I don't have it's not a 2-by-2 matrix, it's a 3-by-3 matrix. So I have to use the original form for the characteristic equation. But what's this going to be? Well, what is A? A is minus 2, I'm going to leave a little space here. 1, 1, 1, minus 2, 1, and finally 1, 1, -2. I subtract lambda from the main diagonal. Minus 2 minus lambda, minus 2 minus lambda, minus 2 minus lambda. And now that equals 0 is the characteristic equation. So the term with the most lambdas in it is the main diagonal. That's always true, notice. Now, each of these, I would be happier writing lambda plus 2. So there would be a negative sign, negative sign, negative sign. The product of three negative signs is still a negative sign because the 3 is an odd number. So it's minus the principal term. The product of these three is minus lambda plus 2 cubed. Now the rest of the terms are going to be easy. There's another term, 1 times 1 times 1. Another term, 1 times 1 times 1. So to that, I add 2. Those 1 and 1 for those two other terms. And now I have the 3 going in this direction, but each one of them has to be prefaced with a minus sign. So minus. What does each one of them come to? Well, this is minus 2 minus lambda when I multiply those three numbers together. And so are the other guys. This is 1 times minus 2 minus lambda. Same thing. So there are 3 of them, minus because they're going this way, minus 3 because there are 3 of them, and what each one of them is negative 2, negative lambda. That's equal to 0, and that's the characteristic equation. Now, it doesn't look very promising. On the other hand, I have selected it for the lecture, so simple psychology should tell you that it's going to come out okay. What I'm going to do is I'm going to expand this. First, imagine changing the signs. I hate to have a minus sign in front of the lambda cube. So let's make this plus, and we'll make this minus, and we'll make this plus. I'll just change all the signs, which is okay since it's an equation, equals 0. That doesn't change its roots any. And now we're going to expand it out. What is this? Lambda plus 2 cubed. Lambda cubed plus. Don't get confused because it's this 2 that will kill you when you use the binomial theorem. If there's 1 here, everybody knows what to do. If there's an a there, everybody knows what to do. It's when that's a number not 1 that everybody makes mistakes, including me. So the binomial coefficients are 1, 3, 3, 1. Because it's a cubed, I'm expanding. So it's lambda cubed plus 3 times lambda squared times 2. I won't explain to you what I'm doing. I'll just do it and hope that you all know what I'm doing. Plus 3 times lambda times 2 squared. Plus the last term is 2 cubed. Okay? And now we have the other term. So all that's plus because I changed its sign. The next thing is negative 2. And then the last thing is plus 3 times minus 2 minus lambda, plus 3 times minus 2 minus lambda. Let's keep it. Okay, so what's the actual characteristic equation? Maybe I can finish it on... I should stay over here instead of recopying all of it. So what are we... well, there's a lot more work to do. Oh, let's see if we can at least write down the equation. So what is it? It's lambda cubed. What's the lambda squared term? It is 6, and that's all there is. How about the lambda term? Well, we got 12 lambda minus 3 lambda. That makes plus 9 lambda. That looks good, but constant terms have a way of screwing everything up. What's the constant term? It is 8 minus 2 minus 6. Ha ha! 0. The constant term is 0. That converts this from a hard problem to an easy problem. Okay, now it's a cinch to calculate stuff. So let's go to this board. I'll continue the work over here. So the equation is lambda cubed plus 6 lambda squared plus 9 lambda is 0. It's very easy to calculate the roots of that. You factor it. So it's lambda is a common factor. And what's left? Lambda squared plus 6 lambda plus 9. That's the sort of thing you got all the time when you were studying critical damping. It is the square of lambda plus 3. Lambda squared plus 6 lambda plus 9 equals 0. So the eigenvalues, the roots, are what? Well, they are lambda equals 0 from this factor, and then lambda equals minus 3 But what's new is that the minus 3 is a double root. That's a double root. Now that, of course, is what's going to cause the trouble. Because for each one of these, I'm supposed to calculate the eigenvector and make up the solution. But that assumed that I had 3 things to get 3 different solutions are. Here I've only got 2 things. It's the same trouble we ran into when there was a repeated root. We were studying second or third order equations, differential equations, and there was a repeated, the characteristic equation had a repeated root, and I had to go into a song and dance and stand on my head and multiply things by t and so on, and then talk very hard arguing why that was a good thing to do to get the answer. Now, I'm not going to do the same thing here. Instead, I'm going to try to solve the problem instead. Okay, let's get 2 points by at least doing the easy part of it. Lambda equals 0. What am I supposed to do with lambda equals 0? I'm looking for the alpha that goes with that, and I find that eigenvector by solving this system of equations. So let's write out what that system of equations is. Well, if lambda is 0, this isn't there. It's just the matrix A times alpha equals 0. And the matrix A is, I never even wrote it anywhere. Blah. All right. I never wrote A. Okay, A is, I thought I would get away without having to do it, but you never get away with anything. It's principle of life. That's A. So if I subtract 0 from the main diagonal, that doesn't do a great deal to A. And the resulting system of equations is those same things, except you got the A1s in there, too. There's 1. A1 minus 2A2 plus A3 equals 0. I'm just subtracting 0 from the main diagonal, so there's nothing to do. A2 minus 2A3 equals 0. Now, I'm supposed to solve those. Of course, we could do it. How do you know how to solve the system of 3 linear equations? Well, elimination. You can always solve by elimination. Now, we are much more sophisticated than that. You all have pocket calculators, so you could use the inverse matrix, right? No, you cannot use the inverse matrix. What will happen if you punch in those coefficients and then punch in A inverse, tell it to take A inverse something? What answer will it give you? 0, 0, 0. I mean, it won't give you any answer. What will it say? It says, I can't calculate the inverse to that matrix because the whole purpose of this exercise was to find a value of lambda such that this system of equations is dependent. The coefficient determinant is 0, and therefore the coefficient matrix does not have an inverse matrix. You can't use that method. In other words, the inverse matrix will never work in these problems because the system of equations you will be trying to solve is always a non-independent system. And therefore, its determinant is always 0, and therefore there is no inverse matrix because the determinant of the coefficients is 0. So all you can do is use elimination or insight, physical insight, and common sense. Now, because I teach differential equations, everybody assumes mistakenly, as I think, that I really know something about them. So I get now and then graduate students, not in mathematics, but some obscure field of engineering or whatever, drift into my office and say, I see you teach differential equations. So do you have got a minute here? I have this different, and then before I can say no, they write their differential equation on the board. And almost invariably, it's nothing I've ever seen before. And they sort of look at me hopefully and expectantly. Okay, so what do I ask them? I don't ask them what they've tried. What I ask them is, where did this come from? What field did it come from? The field it came from, because each field has its own little tricks. It gets the same differential equations all the time and has its own little tricks for solving them. You should do the same thing here. You say, well, look, of course we can solve this. By now, probably, most of you have solved it just by inspection, just by sort of psyching out the answer. But a better way is to say, look, suppose we had the solution. What would the solution look like? Well, it would look like A1, A2, A3, whatever the values of those variables were, which gave me the solution to the equation, times e to the 0t, right? Well, what's this? E to the 0t is 1 for all time, and therefore this is a constant solution. So what I'm asking is to find a constant solution. Now, can I, by inspection, find a constant solution to this? If so, it must be the 1. Well, there's an obvious constant solution. All the cells have the same temperature. If that's the true, then there's no reason why it should ever change as time goes on. So the physical problem itself suggests what the answer must be. You don't have to solve equations. So, in other words, any constant like 1, 1, 1. Well, could it be 20, 20, 20? Yeah, that's a constant multiple of 1, 1, 1. So that's included. My basic constant solution, therefore, is simply 1, 1, 1 times e to the 0t. You don't have to include e to the 0t because it's 1. Now, just to check, is 1, 1, 1 a solution of these equations? Certainly is. 1 plus 1 minus 2 is 0 in every case. The equations are essentially the same, except they use different variables. Okay, so by inspection, or if you like, by elimination, but not by finding the inverse matrix, you solve those equations, and we've got our first solution. Now, let's go on to the second one. Okay, for the second one, we're going to have to use the eigenvalue lambda equals -3. And now what's the system of equations? Well, now I have to take this, and I have to subtract -3 from the diagonal elements. Well, -2 minus -3 is +1, right? Got that? So each of the diagonal elements, after I subtract -3, turns into +1. And therefore, the system becomes, that system, the system I have to solve is A1 plus A2 plus A3 equals 0. And what's the second equation? Ta-da! Symmetry is preserved. If that's what, all the equations are essentially the same except for the names of the variables, so they all must give me the same things after I subtract -3 from the main diagonal. Well, that's what we call a dependent system of equations. You know, all I have is the same equation repeated twice. But I still have to solve it. Now, what you see is that there are lots of solutions to this. Let me write down one of them. For example, suppose I made A1 equal to 1, and I made A2 a 0, then A3 would be -1. So here's a solution. That's the eigenvector. And with it, I can make the solution by multiplying by e to the -3t. So there's a solution. But that's not the only alpha I could have chosen. Suppose I chose this one instead. Suppose I kept this 1, but this time made A3 0. Well, in that case, it would be A2 that had to be -1. Now, is this essentially different from that one? It would still be multiplied by e to the -3t. But don't be fooled by the e to the -3t. That's our scalar. That's not what's essential. What's essential is the content of these two vectors. Is either one a multiple of the other? The answer is no. Therefore, they are independent. They're pointing in two different directions in 3 space, these two vectors. And therefore, I have two independent solutions just by picking two different vectors that solve those 3 equations. So this is also a solution. If I call this the eigenvector alpha 1, then I ought to call this one the alpha 2. Now, hey, we can keep on going to this. I don't know. Aha. Okay, why not make the first one 0 and then negative? Well, what would happen if I made the first one 0 and then 1 and minus 1? The answer is this one is no longer independent of those two. I can get it by taking a combination of those two. Do you see what combination I should take? This one minus that one. This guy minus that guy gives me that guy. Isn't that right? 1 minus 1, 0 minus minus 1, minus 1 minus 0. So this is not a new one. It looks new, but it's not. I can get it by taking a linear combination of these two. It's not independent of them. And that would be true for any other possible solution you could get to these equations. Once you found two solutions, all the others will be linear combinations of them. Okay, so where I can't use that one, it's not new. And the general solution, therefore, will be a combination. C1 times that one, plus a constant times this one, plus the first one that I found, C3 times 1, 1, 1, e to the 0 t, which I don't have to write in. That's the general solution to the system, x1, x2, x3. What happens as time goes to 0? As time goes to infinity, regardless of what the values of the c's are, of these two c's, this term goes to 0, that term goes to 0, and what I'm left with is a constant solution. So all of these solutions tend to the solution where all the cells are at the same temperature. Well, okay. Now, of course, there must be some vocabulary word in this. There is. There are two vocabulary words. So, this is a good eigenvalue. There are also bad eigenvalues. This is a good repeated eigenvalue, but good is not the official word. An eigenvalue like this, which is repeated, but where you can find enough eigenvectors. So if lambda is repeated, is a repeated eigenvalue, it occurs multiply in the characteristic polynomial as a root, but I don't want to have but you can find enough eigenvectors. Enough, but the grammar is already hopeless. Repeated order. All right, forget the but. You can find enough independent eigenvectors to make up eigenvectors to make up the needed number of solutions, the needed number of independent solutions. For example, if it's repeated twice, if it's repeated once, that is, it occurs doubly, then somehow I got to get two solutions out of that, as I was able to here. If it were repeated if it occurs triply, I got to get three solutions out of it, so I would look for three independent eigenvectors and hope I could find them. That's the good case, because it tells you how to make up as many solutions as you need. And this kind of eigenvalue is called in the literature complete. It's called a complete eigenvalue. Now, how about the kind in which you can't? Well, unfortunately, all my life I've called it incomplete, but which seems to be a perfectly reasonable thing to call it. However, terminology changes slowly over time. The notes, because I wrote them, call it an incomplete eigenvalue, but the accepted term nowadays is defective. I don't like that. It violates the Eigenvalues with Disabilities Act or something, but it's not But I have to give it to you because that's the word I'm going to try to use from now on, at least if I remember to use it. It would be the word, for example, used in the linear algebra course, 1806, plug, plug, defective otherwise. So a defective eigenvalue is one where you can get one eigenvector, but if it's a double, for example, if it's a double eigenvalue, it's defective if you can get one eigenvector that goes with it, but you cannot find an independent one. The only other ones you could find are multiples of the first one. Then you're really in trouble because you just don't have enough solutions that you're supposed to get out of that, and you got to do something. Okay, so what you do is turn to problem 2 on your problem set and solve it, because that tells you what to do. And I even give you an example to work. So B, problem 2, that little matrix has a defective eigenvalue. It doesn't look defective, but you can't tell. It is defective. But you nonetheless will be able to find 2 solutions because you'll be following instructions. Okay, now the only other thing I should tell you is one of the most important theorems in linear algebra, which is totally beyond the scope of this course and is beyond the scope of most elementary linear algebra courses as they're taught around the country, but of course not at MIT. But it nonetheless is the last theorem in the course, so that means it's liable to use stuff. It's the theorem, it goes by different names. Sometimes it's called the principal axis theorem. Sometimes it's called the spectral theorem, blah, 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 blah. But anyway, what it says is, if A is a real n by n matrix, which is symmetric, notice symmetric matrix is, it's one, the formal definition is, it's equal to its transpose. What that means is, if you flip it around the main diagonal, it looks just the same as before. Where, somewhere on this board, is right there, in fact, is a symmetric matrix. What happened to it? Oh, yeah, right here. Right here was the symmetric matrix. I erased the one thing which I had to have. Okay. All right. Minus 2, 1, 1. 1 minus 2, 1. 1, 1 minus 2. That was our matrix A. That matrix is symmetric because if I flip it around the diagonal, it looks the same as it did before. Well, not exactly. The ones are sort of lying on their side, but you have to take account of that. Is that right? Yeah. Well, the 2s are backward. Okay, you know what I mean. So put that element there, this one here, that one there, and that one. Exchange these 2. Notice the diagonal elements don't all have to be minus 2 for that. No matter what they were, they're the they're the guys that aren't moved when you do the flipping, and therefore there's no condition on them. It's these other guys. Each guy here has to use the same guy there. This one has to be the same as that one, and so on. Then it will be real and symmetric. Okay, so if you have a matrix which is real and symmetric, like the one we've been working with, the theorem is that all its eigenvalues are complete. That's a very unobvious theorem. All its eigenvalues are automatically complete. Are complete. And it's a remarkable fact that you can prove that without it purely generally, with a certain amount of pure reasoning, no calculation at all. But it has to be true, and it is true. You'll find there are whole branches of applied differential equation, equilibrium theory, for all the matrices that you deal with are always symmetric, and therefore this repeated eigenvalues is not something you have to worry about finding extra solutions. Okay. Well, I guess that's the end of the first part of the lecture, so I've got a third of it. Ooh, left. Good. Let's talk fast. So I'd like to, in the remaining time, explain to you what to do if you get complex eigenvalues. Now, actually, the answer is follow the same program. In other words, if you solve the characteristic equation and you get a complex root, follow the program, calculate the corresponding complex eigenvectors. In other words, solve the equations. Everything will be the same except that the eigenvectors will turn out to be complex, that is, have complex entries. Don't worry about it. Then form the solutions. The solutions are now going to look, once again, like alpha times e to the a plus bi t. So this will be complex, and that will be complex too. This will have complex entries. And then finally, take the real and imaginary parts. Those will be real, and they will give real and two solutions. In other words, the program is exactly like what we did for second-order equations, differential equations. We used the complex numbers, got complex solutions, and then at the very last step, we took the real and imaginary parts to get two real solutions out of each complex number. So I'd like to give you a simple example of working that out. And it's the system x equals x prime equals x plus 2y and y prime equals minus x minus y. Because it's springtime, even it doesn't feel like spring, but it will this weekend. It's getting warmer. So, and since when I can't do, when I'm too tired to make up problem sets for you, late at night I watch reruns of Seinfeld. I'm from New York. It's just in my bloodstream. So of course, the most interesting character on Seinfeld is George. So we're going to consider Susan, who's the girlfriend who got killed by licking envelopes, poison envelopes, and George, who carried on their love affair until Susan was disposed of by the writers by this strange death. And we're going to consider X as modeling Susan's love for George. Susan's love for George. That's X and George's love for Susan. That will be Y. Now, I don't mean the absolute love. So if X and Y are 0, I don't mean that they don't love each other. I just mean that that's the equilibrium value of the love. Everything else is measured as departures from that. So 0, 0 represents the normal state, the normal amount of love. If love is measured, I don't know what love units are, but hearts, I guess, and 6 hearts, let's say. Now, in what sense does this model it? Well, this is a normal equation, and this is a neurotic equation. That's why this is George, and this is Susan, who seemed very normal to me. You know, Susan's a normal person. When Y is positive, that means George seems to be loving her more today than yesterday, and her natural response is to be more in love with him. Yeah, that's what most people are. If Y is negative, you know, hey, what's the matter with George? You know, you don't feel so good. Well, maybe something wrong with him. You know, she gets a little mad at him, and this goes down. X prime is negative. And the same way, why is this positive? Well, it's because, again, it's a psychological thing, but all the world loves a lover. When Susan's in love, as she feels X is high, that makes her feel good. And, you know, she loves everything, in fact, not just George. It's one of those things. You all know what I'm talking about. Now, George is, of course, is what makes the writers happy. George is neurotic, and therefore he has exactly the opposite. Okay, he sees one day that he feels more in love with Susan than he was yesterday. Hey, does this make him happy? Not at all. Not at all. Why? It makes Y prime more negative. Why? because all he can think of is that, my God, suppose I'm really in love with this girl, but suppose I marry her, you know. Oh, my God, 40 years of seeing the same person at breakfast all the time. I must be crazy. And so it goes down. All right, so here's our neurotic model, and the question for differential equations is, what do the solutions to that look like? In other words, how does, in fact, their love affair go? Now, there's a reason why the writers picked that model, as you'll see. It means they were able to get a year's worth of episodes out of it, and why is that so? Well, let's solve it. The characteristic equation is lambda squared. The trace, the matrix that governs this system is A equals 1, 2, -1, -1, right? The trace of that matrix, the sum of the diagonal elements, is 0. So there's the 0 lambda here. The determinant, which is the constant term, is -1 minus -2, which is +1. So the characteristic equation, by calculating the trace and determinant, is lambda squared plus 1 equals 0. Ta-da! The eigenvalues are plus or minus I. Now, you don't have to pick both of them, because one will lead to essentially the same. So the negative one will lead to essentially the same solutions, but with negative signs. So either one will do, just as when we solve second-order equations. The system for finding the eigenvectors, but we're going to have to accept a complex eigenvector. What's the system going to be? Well, I take the matrix and I subtract I, so we'll use I. Subtract I from the main diagonal. So the system is 1 minus I times A1 plus 2A2 is 0. And let's, for good measure, write the other one down, too. It is negative A1 plus minus 1 minus I. Okay? Minus 1 minus I. A2 is 0. Okay, then what's the solution? Well, you get the solution by the usual way. Let's take A1 equal to 1. Take A1 equal to 1, then what's A2? A2 is 1 minus I divided by 2 from the first equation. So the solution, the complex solution, is 1 minus I over 2 times e to the it. Now you have to take the real and imaginary parts of that. Okay, now this is the only part which technically I would not trust you to do without having someone show you to do it. What do you do? All right. You have to, well, of course, you know how to separate the real and imaginary parts of that. It's the first thing. To separate the vectors, I don't know how to explain this, just watch. The real part of it is 1, 1/2. The, is that negative? It should be negative 1, so minus this plus that. Because I didn't put it on the right sign. Okay, so it's minus 1/2 plus I times 0, 1/2. Anybody want to fight? 1 plus I times 0 minus 1/2 plus 1/2 times I. Okay, so how I did that? Okay, when you do these problems, you do it the same way. But don't ask me to explain what I just did. So here it's cosine t plus I sine t. And so the only things is to take the real. Let's take, beg pardon, question, is something wrong? Okay. The real part, so the real part will give me one solution. The imaginary part will give me another. Since I have a limited amount of time, let's just take the real, calculate the real part. What is it? Well, it's this. It's 1 minus 1/2 times cosine t. I squared is negative 1. So minus 0, 1/2, the negative 1 from the I squared times sine t. Now, what solution is that? That is, so this is x, y. So what it is x equals, take the final step. It doesn't have to look like that. X equals cosine t. Do you see that? X equals cosine t plus 0 times sine t. What is y? Y is minus a half times cosine t minus a half times sine t. Cosine t plus sine t. Now, you may have the pleasure of showing eliminating x and eliminate t, you get a quadratic. That's a quadratic polynomial in x and y equals 0. This is an ellipse. As t varies, you can see this repeats its values at intervals of 2 pi. This gives an ellipse. And if you want to use a little program, computer program, that linear phase, this isn't in the assignment, but the ellipses look like this. And they go around that way. And that's the model of George and Susan's love. X, Susan. Y, George. They go round and round in this little love circle, and it stretches on for 26 episodes.